Hashtag AI Training Cost Breakthroughs, long-form tutorial script. You're training AI models wrong, and it's costing you thousands of dollars you don't need to spend. The technology industry just experienced a seismic shift, and most people haven't realized it yet. In this tutorial, I'm breaking down the 3 major breakthroughs that just slashed AI training costs by up to 70%, and how you can leverage them today. Let me start with the elephant in the room. For years, training enterprise-grade AI models meant renting expensive GPU clusters, paying astronomical cloud compute bills, and hoping your model converged before your budget evaporated. According to Meta's research from early 2024, the average cost to train a large language model hovered in the millions. But that's changing fast. The problem isn't theoretical anymore, it's practical. If you're running an AI project, whether you're a startup, educator, or enterprise, your training infrastructure is probably inefficient. You're likely burning compute cycles unnecessarily. You're probably not using quantization. You're definitely not leveraging mixture of experts architecture. And worst of all, you don't know what you're missing. Here's what we're covering today. First, we're tackling quantization techniques that reduce model precision without destroying accuracy. Second, we're exploring knowledge distillation, basically teaching smaller models to mimic larger ones. And third, we're diving into distributed training optimization that cuts your wall clock time in half. Let's jump into step 1, understanding quantization. Open your model training framework. Whether you're using PyTorch, TensorFlow, or any major platform, navigate to your model configuration panel. Look for the precision settings drop-down menu. You'll see FP32, that's full 32-bit floating point. That's your baseline, and it's expensive. Switch to FP16, or 16-bit floating point. According to NVIDIA's optimization documentation from 2024, this single change reduces memory requirements by 50%. Your models train faster. Your costs drop immediately. But here's the critical part, and this is where most people fail: you need to implement loss scaling. Without it, you lose numerical stability. In your training loop, before your backward pass, enable automatic mixed precision. Most frameworks call this AMP. PyTorch calls it torch.cuda.amp autocast. TensorFlow has tf.keras.mixed_precision. These are your golden tools. Now let's get into the real game changer, knowledge distillation. This is step 2, and it's where you'll see dramatic cost reduction. The concept is beautifully simple. You take your large, expensive model, your teacher model, and you train a smaller, faster student model to replicate its behavior. The student model costs a fraction to train. Here's how it works practically. First, load your pre-trained teacher model. This is your reference point. Second, initialize a smaller student architecture. We're talking significantly smaller, sometimes 20 to 30% of the original size. Third, create a distillation loss function. This combines 2 objectives: matching the student's predictions to the ground truth labels, and matching the student's output distributions to the teacher's output distributions. The temperature parameter matters here. Set it between 3 and 20 depending on your model complexity. Per OpenAI's research findings through early 2024, temperature values around 5 typically yield optimal results. Run your training pipeline using this combined loss. You'll watch something remarkable happen. Your smaller model learns to approximate your larger model's capabilities at a fraction of the computational cost. We're talking 85 to 95% performance retention with 50 to 70% reduction in training cost. If you're finding this valuable, hit that subscribe button. We post tech tutorials daily, and if you don't subscribe, you'll miss the infrastructure optimization tricks that could save your organization hundreds of thousands of dollars. Now we're into the advanced territory. Step 3, distributed training optimization. This is where your architecture choices matter enormously. You have 3 architectural paradigms to consider. First, data parallelism. Your model lives on one GPU, but your data splits across multiple GPUs. Each GPU processes different batches, computes gradients, and synchronizes them. This works beautifully until your model gets too large for a single GPU. It hits a wall. Second, model parallelism. Your model splits across multiple GPUs. Different layers or components run on different hardware. This works, but synchronization overhead becomes brutal. Your GPUs sit idle waiting for each other constantly. Third, and this is where the breakthrough lives, pipeline parallelism combined with mixture of experts. Pipeline parallelism staggers your computation so different GPUs work on different samples simultaneously, eliminating idle time. Mixture of experts means different subsets of your model neurons activate based on the input. You're not computing the entire model for every token. You're computing only the relevant experts. Per recent distributed training studies from major AI labs in early 2024, this combination reduced training time by 40 to 60% compared to traditional data parallelism. Implement this in your codebase. If you're using PyTorch, look at the torch.distributed module. You'll see distributed data parallel for data parallelism. For pipeline and ML, you're likely using frameworks like Megatron LM or specialized libraries like DeepSpeed. DeepSpeed, developed by Microsoft, specifically implements these optimization techniques. Open the DeepSpeed configuration JSON file. You'll see parameters like number_experts, expert_parallel_size, and pipeline_parallel_size. These control your optimization profile. Step 4 dives deeper, gradient accumulation. Your batch size is limited by GPU memory, right? Gradient accumulation lets you simulate larger batches without increasing memory consumption. Process smaller batches, accumulate their gradients over multiple steps, then apply the update. This improves training stability and final model quality without hardware investment. Step 5, Activation checkpointing. Here's what happens normally. During backpropagation, you need to access activations from every layer. They consume massive amounts of memory. Activation checkpointing recomputes activations during backpropagation instead of storing them. You trade memory for compute time. Per NVIDIA's documentation, this reduces peak memory usage by 30 to 40%, letting you fit larger models or batches into your hardware. Step 6, Learning rate scheduling and warm-up. Don't just set your learning rate and leave it. Implement a warm-up phase where learning rate gradually increases from near zero to your target value over the first few percent of training. This stabilizes early training. Then implement a decay schedule. Cosine annealing typically works brilliantly where learning rate gradually decreases. This convergence technique, well documented in transformer research, can reduce total training time by 10 to 15%. Step 7, Monitoring and early stopping. Use TensorBoard or weights and biases to monitor your validation loss. Implement early stopping. When validation loss plateaus for a specified number of evaluation steps, stop training. You're not paying for compute cycles that aren't improving your model. This is pure waste elimination. Step 8, Cloud cost optimization. If you're using cloud platforms, this matters enormously. Choose spot instances or preemptible VMs. They're 70 to 80% cheaper than on-demand pricing. Your training might get interrupted, but implement checkpointing to resume seamlessly. Most frameworks support this natively. Now let's talk pro tips. First, batch size tuning. Many people assume bigger batches are always better. They're not. Find your sweet spot, usually between 256 and 1024 for transformer models, where you balance training stability and convergence speed. Second, leverage pre-trained models whenever possible. Fine-tuning costs a fraction of training from scratch. According to transfer learning research documented through early 2024, fine-tuning pre-trained models reduces training cost by 70 to 85% compared to training from random initialization. Third, use lower precision training from the start. Don't train in FP32 and convert later. Start in mixed precision. Fourth, containerize your training pipeline. Use Docker to package your code, dependencies, and configuration. This ensures reproducibility and makes cloud deployment seamless. Fifth, implement distributed logging. Track not just loss, but GPU utilization, memory consumption, and compute efficiency metrics. This data guides your optimization decisions. Here's something most people miss: architectural efficiency matters as much as training optimization. Consider replacing traditional transformer layers with more efficient variants like flash attention, which reduces attention computation from quadratic to linear complexity. Per the flash attention paper released in 2023, this technique reduces training time by 20 to 30% while maintaining accuracy. Another pro tip: monitor your GPU utilization. If it's below 85%, your training pipeline has bottlenecks. Usually it's data loading. Implement pre-caching, parallel data loading with number_workers parameter, and prefetching to keep your GPUs fed. One final advanced move: use tensor cores effectively. Modern GPUs have specialized hardware for specific precision types. A 100 GPUs accelerate TF32, FP16, and Float16 operations dramatically compared to FP32. Float16, in particular, offers the precision range of FP32 with FP16's memory efficiency. It's become the standard in cutting-edge training pipelines. Let me bring this together. You came here thinking AI training was expensive and complex. It is. But it doesn't have to be anymore. These breakthroughs, quantization, knowledge distillation, distributed training optimization, and the implementation techniques we covered, these aren't hypothetical. They're being deployed at scale right now by major research labs and enterprises. The cost reduction is real. We're not talking about marginal improvements. We're talking about 70% reductions in training costs, 50% reductions in training time, and significantly better model performance when you implement these correctly. Your next step is simple. Pick one technique. Master it. If you're training models, start with mixed precision quantization today. Enable AMP in your training script. Measure your memory reduction and speed improvement. Then layer in another technique next week. Remember, we help you navigate your tech journey with confidence. These tools, these techniques, these architectural decisions, they're your navigation tools. You now have the knowledge to optimize, to reduce costs, and to train models more efficiently than 95% of practitioners. If this tutorial moved you closer to mastery, subscribe. We post tech tutorials daily. You'll master these platforms. You'll stay ahead of the curve. And you'll build AI systems that don't cost a fortune. Go forth. Train smarter. Build better.